Hello, grade sevens. In today's lesson, which is actually the last lecture for the Planet Earth unit of study, we are going to look at different methods that can be used to identify the age of both rocks and fossils, and then briefly touch on the geologic time scale, which is essentially an outline showing what kind of organisms existed in specific periods of time. Learning outcomes for today are to 1. Identify and explain the purpose of different tools and techniques used in the study of Earth. Specifically for that, we'll look at techniques used to figure out the age of rocks. 2. Explain and apply methods used to interpret fossils. So for that outcome, we'll look at methods used to figure out the age of fossils. And then 3, describe patterns in the appearance of different life forms as indicated by the fossil record. So that will be talking about the geologic time scale. Let's start off with something called the principle of superposition. What the principle of superposition can do is it can be used to determine the relative age of layers of rock. And what the principle states is that in undisturbed layers of rock, I'll come back to that undisturbed in a moment, the oldest layers are always found on the bottom, and the younger layers are always found on the top. Let's draw a picture to illustrate this point. Okay, so let's say that a bunch of sediment goes on top of the Earth's surface, and over a long period of time, other sediments come on top, they crush it, water might go through and act as a cement to make the different sediments come together. So we're going to get one rock layer. We'll call this rock layer 1. This layer forms, and then afterwards, more sediments pile on top of this one. And those sediments eventually get crushed together. Maybe they get cemented together, and you get a second rock layer, number 2. Then later on, more sediments pile up on top of layer 3. They get crushed together, cemented together, and then you get rock layer number 3. What the principle of superposition tells me is it only tells me the relative age of the rocks. When I say relative age, it does not tell me the exact age of the rock. For example, what I know is the bottom layer, well, that's where all the sediments collected first. So in these 3 rock layers, I know that layer number 1 would be the oldest rock layer. Layer number 3, well, that was the last layer where you had sediments combining together, getting cemented together to give you this layer. So this top layer would be the youngest rock. The problem here is that I don't actually know how old the rock in layer 1 is and how old the rock in layer 3 is. The only thing I can say is that the rock in layer 1 is older than the rock in layer 3. And that's what I mean by the relative age of the rock. Relative age means we can just compare 2 things. For example, if I was to compare my age to your age, my age would be, relatively speaking, my age would be older than your age. That doesn't tell us how old I am or how old you are, but at least gives us an indication as to who is older. And that's what our principle of superposition tells us. The youngest layers of rock would be on the top, the oldest layers would be further below. This only occurs, though, or this is only true if the rock layer is undisturbed. So for example, this rock layer could get disturbed. We could have an earthquake occur, and we have a fault line. So there's a big break in the rock. Big break in the rock here. And then a bunch of sediments kind of come in and they fill this little break up. We'll call this number 4. even though sediment does go all the way down to the bottom of this crack right here, it does not mean that rock layer 4 is older than number 3. The rock layer was disturbed. There was a crack that formed in the rock, and then a bunch of sediments were able to go very, very far down into the crack as a result of that. So in this case, it would still be the oldest layer is the bottom layer number 1 here, and the youngest layer would actually be the rock that accumulates into this crack. So just one thing to be aware of with the principle of superposition. As long as my rock layer is undisturbed, older layers are on the bottom and the younger layers are on the top. We can take this one step further, and we can also determine what the age of a fossil is, relatively speaking. And if we're not actually identifying the exact age and just identifying which fossil is older than which, again, that deals with relative age. And the word we'd use to describe this is relative dating. For example, if I had a rock layer, again, so let's just sketch this. Let's just do 2 of them here. So you've got rock layer 1, rock layer 2. And let's say we dug up a fossil in rock layer 1. So I can't draw anything but I can't even draw a fish. Okay, let's be honest about that. But let's just draw that arrow again to indicate that's my fish. Then here's another fossil, petrified rock fossil of a fish. Relative dating states that the age of the fossil is determined by the position in the strata or the layer of rock. So if I dug up these 2 fossils, so this fossil, number 1, and this fossil, number 2, because fossil 2 is in the layer of rock that is further down, that would tell me that this fossil is older and the fossil in the upper layer is younger. So I could just simply state that fossil 1 is younger than fossil 2. It doesn't tell me the exact age of them, but I have at least a relative comparison in terms of the age. Index fossil. This is a little bit tricky to explain. An index fossil is when you have a fossil that is widespread on the Earth for a short period of time. It can be used to tell me something about the relative ages of layers of rock. Okay, let me give an example of this. So let's say that there was a fossil and it existed for only a very short period of time. I'm going to draw the rock layers at 2 portions on the Earth. So we'll say we have North America. And I'm just going to draw some rock layers. I'll do 3 of them. So we have layer 1, we have layer 2, and we have layer 3. And I'll draw my horrible fish fossil in layer 2. Now, let's compare this to somewhere in, I'll just pick a different continent. We'll say in South America. I'll do 3 rock layers again. Rock layer 1, 2, 3. We'll number them. 1, 2, 3. And then I'm going to draw this fossil, which I'm going to, again, I'm calling an index fossil. Okay, so I dig up a bunch of rock in North America, and I find this index fossil in rock layer 2. In South America, I dig up a bunch of rock, and I find this index fossil in rock layer number 3. Now, an index fossil only existed for a very short period of time. And what it can be used to do is it can be used to tell me how old the rock actually is. So if I dug up this index fossil in layer 2 in North America, and I dug up this index fossil in layer 3 in South America, what this would tell me is it would tell me, because the index fossil only existed for a short period of time, it would tell me that the age of rock 2 would be equal, well, roughly equal, probably not perfectly equal, but roughly equal to the age of rock layer 3. So I'm using where I find the index fossil to make a comparison as to how old these rock layers are. And that's what an index fossil is. Now, as I mentioned, the methods for identifying the age of rocks and fossils on the previous slide, they don't tell us exactly how old the rock or the fossil is. So what we want is we want a method that does give us an actual numerical value in terms of what the age of the rock or the fossil is going to be. And this is what the absolute dating method is going to do. It's going to give us an exact age, or I won't say exact, but like a reasonably accurate age as to the age of the rock or the fossil. We can break this into two categories. One method is going to be applying to age of rocks. One method is going to apply to age of fossils. The way we can determine the exact age or an accurate age for a rock is we can look at the amount of elements that we can find in the rock. Depending on what percentage of elements we find in the rock, we can determine what the exact age is. The way we do this is we need to know a little bit about something called the half-life of the rock. The half-life of a material is the amount of time it takes a radioactive element to reduce in mass by 1/2 and turn into other elements. Okay, I'm going to draw a picture to illustrate the point of half-life. There are certain elements on the periodic table that are not stable. Not stable means that they tend to, over time, decay into other elements. And I'll give one example. So uranium. We'll just use the element symbol, which is U. Uranium is a radioactive element. Radioactive elements tend to decay or eventually turn into another type of element. The element that uranium eventually turns into is lead. The element symbol for lead is Pb. I believe it's Latin for, believe this or not, plumbum or plumbus. Okay, so this uranium, it decays into lead. Now, let's use this to explain half-life. So let's say that we have 100%, we have a rock, and in that rock, I have 100% of the element uranium. What this element is going to do is this element is going to, over a certain period of time, it's going to decay into lead. Let's say that sometime later, this uranium has decayed into 50% of it is now lead. So uranium radioactive has decayed into 50% lead. So what that means is that 50% of the uranium has turned into lead, and the other 50% of the uranium has not turned into lead yet. It's still uranium. If you look at this right here, what's happened is I have 100% of uranium, and this is turned into 50% of uranium. So what's happened is I only have 1/2 of the uranium left. The time it takes for you to start with 100% of your element and then to only have 50% of it is what we call a half-life. And going back to the definition, a half-life is the amount of time it takes a radioactive element to reduce in mass by 1/2 and turn into other elements. So again, we start with 100% of uranium. After one half-life means I only have half of my original mass now. So now I have half of the uranium, and then I'm left with 50% of lead. 50% of it turned into lead. Well, let's go through another half-life and see what happens. So we'll go through another half-life. If you start with 50% of uranium and you go through one other half-life, a half-life is the time it takes for you to have 1/2 of your mass. So 1/2 of 50% would then be 25%. If I have 25% of uranium, then I now have much more lead. I need these numbers to add up to 100%, so I now have 75% of lead. Let's go through another half-life. So if you start with 25% of uranium and you go through one half-life, then one half-life would mean that the mass of uranium is going to get cut in half. So half of 25% would be 12.5% of uranium. Then how much lead would we have now? Well, more of the uranium's turned into lead. So now we'd have 87.5% of lead. Okay, and that's another half-life. Now you might be wondering, okay, that's great. So half-life is just the time it takes for the mass of your element to get cut in half. How does this tell me the age of a rock? Well, let's say we dug up a rock. Okay, we dug up a rock. So we dig up a rock. And we figure out through some means that in this rock has 12.5% of uranium and it has 87.5% of lead. So what I know right here is I know the percentage of elements I have in the rock. Now, how can I use this to figure out what the age of the rock actually is? Well, the question you'd want to ask yourself is, based on the percentages of these elements, how many half-lives have passed? Well, if you look at our little chart right here, the total number of half-lives that have passed has been 3. Three half-lives have passed. Now, we need to know what the actual half-life of uranium is, and I believe the half-life of uranium is 4.5 billion years. So to go from 100% of uranium to only having 12.5% of uranium, we went through 3 half-lives. So the way I'd figure out the age of the rock is I'd take the number of half-lives, which is 3, and then multiply by the time for one half-life. So I'd go 3 times 4.5 billion. And I believe 3 times 4.5 billion is, I want to say 13.5 billion years old. So that's what we do. We dig up the rock, look at the percentage of each element inside the rock, And then we ask ourselves, well, how many half-lives have passed? And then once we know how many half-lives have passed, if we multiply by the time of one half-life, we can figure out how old the rock actually is. Okay, let's go through some more of these summary notes. If you're a bit confused about this, I'll go through a few more of these flow charts, and then at the end of the lesson, I'll go through a couple more examples if you're a bit unclear as to how you can figure out the age. I already talked about uranium. So uranium has a half-life of 4.5 billion years. It's radioactive, and radioactive substances, they eventually decay into some other kind of element. And the other element it decays into is lead. I should point out, by the way, that the calculation I performed was unrealistic. Because I said the age of that rock was 13.5 billion years old. Well, I think the Earth itself is only 4.6 billion years old, so there's no way that 3 half-lives could have actually passed for uranium. But just for the purpose of explaining how half-life works, I just assumed that I could go through 3 half-lives. But again, I think the age of the Earth is 4.6 billion years old. Okay, so radiometric dating can be used to figure out the age of a rock by looking at the elements in it. Radiocarbon dating, it's just a special type of radioactive dating. However, it relates to fossils. In a fossil, in the remains of a fossil, I guess that could be like the tissues or cells or bones or whatever. Same thing. If we dug up a fossil, we could take the bone or tissue cells and we could figure out, well, what percentage of a certain element is inside this bone. And based on those percentages of the element, we can again ask ourselves, well, how many half-lives have passed? And then we can figure out what the age of the actual fossil or the animal was. In the tissues and cells of animals, there is an element called carbon-14. It's an isotope of carbon. It has a half-life of 5,730 years. It is also unstable, and over time, it will decay automatically into nitrogen gas. Let's go through another one of these examples of a flow chart. Now, this time around, let's say that we started off with, instead of a percentage, let's use like an actual mass of substance. So I'll say we have 20 kilograms of, we're going to use C for carbon and the element symbol N for nitrogen. So let's say we have 20 kilograms of carbon. Let's follow through a bunch of half-lives. If I pass through 1 half-life of carbon, that'd be the time it would take for me to only have 1/2 the mass of carbon. So 1/2 the mass of 20 would be, you have 10 kilograms of carbon left. What happened to the other 10 kilograms of carbon? If I started with 10 and I started with 20 and I only have 10 kilograms of carbon, what happened to it? Well, the rest of it decayed into this nitrogen gas. So 10 kilograms of nitrogen. Let's go through another half-life. If you start with 10 kilograms of carbon and you go through 1 half-life, you would have 1/2 of that mass. So 1/2 the mass of carbon, if you have 10 kilograms of carbon, would be 5 kilograms of carbon. If you have 5 kilograms of carbon, then you'd question, okay, if I started with 20 and I have only 5 kilograms of carbon left, what happened to the other 15 kilograms of carbon? Well, it decayed into that other element. So that other element would be 15 kilograms of nitrogen. Let's say now we want to figure out the age of this rock. So what would happen is we dig this rock up, or not rock, dig up this fossil. I'll say dig up fossil. And when we analyze how much mass we have of each element in the fossil, we notice we have 5 kilograms of carbon and 15 kilograms of nitrogen. So what we want to do is we want to figure out how many half-lives of carbon we have gone through. Well, look at our flow chart here. In our flow chart, we've gone through 2 of them. When we go through 1 half-life, that would have been 5,730 years. If you go through another one, 5,730 years. The way to figure out the age of the fossil would be take the number of half-lives, which is 2, and then multiply by the time of 1 half-life. So the time of 1 half-life would be 2 times 5,730 years. If I rounded 5,730 to 6,000, the age would be approximately 12,000, but I'll just quickly perform this calculation. So 2 times 5,730 would be 11,460 years old. Okay. And like I said, if this is a bit confusing, then at the end of the lesson, if you want, you can stick around and I'll just go through a couple more examples of how we can use the amount of substance or of element in our rock or fossil to figure out the age. Before we do that, though, let's just briefly touch on the geological timescale. The geological timescale is a division of the Earth's history into smaller units based on the appearance of different forms of life. This picture shows a geological timescale, and it shows it based on, so we would be at the very right end of the scale here. So this is how many billion years ago. So humans existed pretty much. I think if you look, if you assume like the Earth was like a 24, like the age of the Earth was 24 hours, like a 24-hour clock. I think humans have existed for maybe like a few seconds of that 24 hours. We've barely been in existence compared to the actual age of the Earth. With the age of the Earth, being, again, identifies in this picture here as being like 4.55 billion years. It's around 4.6 billion years old. And all the geological timescales, it shows us what kind of organisms existed at different periods of time. And there's certain organisms that did exist in certain periods. We can actually take the time scale and we can break it down in terms of specific units of time, going from an aeon to an era to a period. Okay, so here's the analogy I'll use, because like the aeon, area, and period, those are huge amounts of time. So let's use something we're a bit more familiar with. Let's take an hour. In 1 hour, you can break it into a bunch of minutes. In a minute, you can break it into a bunch of seconds. So if I used hours, minutes, and seconds, if I organized these times from largest to smallest, it would go from an hour to a minute to a second. Now, for the geological timescale of the Earth, we're dealing with like 4.6 billion years old. So we need like much, much larger time units. And that's why we use these units that are referred to as an aeon, an era, and a period. Okay, let's look at this in a bit more detail. An aeon will be the largest period of time. So if you look right here, this era, I'm going to totally mispronounce this, Phanerozoic. If you look at the actual time here, it looks like it existed for, or the time of this aeon would have been 570 million years old. We can take this era, this aeon, we can break it into some smaller eras. So let's take this one, the Mesozoic era, Mesozoic. Again, I'm not totally sure how to pronounce this. An era is a smaller period of time. So this era would only go from 66 million years old to 240 million years old. So that would be, I believe, like 174 million years. If you went 240 minus 60, I think that's right. 174. And then we can break it into even smaller time units. So that would be into a period. So let's focus on what we're most familiar with. Jurassic time period would be the time period where we have dinosaurs existing in. But I think they might span some of these other periods as well. I'm not totally sure about that. And the Jurassic time period would only go from 138 million years old to 205 million years old. So again, as we go from aeon to era to period, we're starting to get into smaller time units. The only other thing I'm going to point out in this chart right here is just what the current era that we live in is. So I think it's like the Cenozoic era. And that's all your geological time scale does, is basically it shows the age of the Earth, and then we break down the age of the Earth into these different aeons, eras, and periods. And there's specific organisms that tended to live or exist in these eras. I think in the first one, the Archean aeon, I don't think many complicated life forms existed. Like maybe like some really, really simple organisms with like not a whole lot of cells compared to the large number of cell organisms we started to see in the Mesozoic era or now the Cenozoic era. All right, so that's the end of the lesson. There are 2 assignments you need to complete. One of them is called Geologic Time. It is an assignment where you're going to need to use the textbook to make reference to. And also there's an assignment that follows that's called Geological Time Skill Builder. That second assignment is going to get into some problems where you have to do some calculations for the age of a rock or a fossil based on the half-life. Now, based on my explanation so far, if you're okay with you think you might be able to figure out the age of a rock and a fossil, then I would just skip what I'm about to talk about right now. If you're still not totally clear about how this half-life works, and just stick around for maybe a few minutes here, and I'll go through a couple of examples. Okay, so let's say this. We'll say, I'm going to go to different pen color. Let's go to blue. I'm going to say example 1. Determine the age of the following rocks or fossils if the following elements were analyzed in each rock or fossil. Okay, so let's do A. We're going to say that we dug up a rock and in that rock, I observed there to be 12.5 grams of uranium and 37.5 grams of lead. So that's the first one. And the second one, We're going to say we dug up a fossil. Instead of using masses here, I'm going to use percentages. So we'll say that we had 3.125% of carbon-14 and 96.875% of nitrogen. Okay, let's go to a different color to do this. To solve this, I need to work backwards. So I'm going to start off by drawing my proportions of these elements on the right-hand side. So let's do A first. So for A, let's say we started off with, as the question tells me, I have 12.5 grams of, not of 8, 12.5 grams of uranium. And 37.5 grams of lead. Now, I want to work backwards. So I got to kind of work backwards to figure out how far do I have to go back to get 100% of my original elements. Let's do this. Okay, so I started off with 12.5 grams of uranium. If I went back a half-life, okay, in the reverse direction, if you go back a half-life, your mass would actually double. So if I go back in time by one half-life, I would take this 12.5 grams and I would double it. So I'd have 25 grams of uranium. Now, how much lead would I have? Well, look at these numbers here. If I add them up, the total mass of these numbers would be 50 grams. So if I went back by half-life, right now have double the amount of uranium, well, I'd have less lead because not as much of the uranium is decayed into the lead yet. Since the total mass needs to be 50, I then have 25 grams of lead. Okay, that adds up to 50 again. Let's go back by another half-life. If I go back by one more half-life, I would double the amount of uranium. So if I double the amount of uranium, I would now have 50 grams of uranium. How much lead do I have? Well, nothing. No lead. This adds up to 50. This is what my rock started off like. My rock started off like 50 grams of uranium and 0 grams of lead. So what I've done is I started by taking a rock, analyzing it based on how much mass of each element is in there, and I started to go back half-lives to figure out how old the rock is. Okay, well let's figure this out now. So how many half-lives have I gone through? Here's one half-life. And here's another half-life. To get the age, you take the number of half-lives that have passed, that's 2, and multiply by the half-life of uranium. The half-life of uranium is 4.5 billion years. So your age would be, 2 times 4.5 would be 9 billion years old. Again, this is not realistic at all because the age of the Earth is 4.6 billion years. There's no way that this rock could actually be this old aside from me just making it like this for the purpose of an example problem. Okay, let's go to part B now. Let's try to figure out what the age of a fossil is. Okay, so we got to work backwards. So let's start off with, we dig up our fossil, we analyze the amount of elements in it, and I have 3.125% of carbon-14. And I have 96.875% of nitrogen. When you add these two numbers up, they should give you 100%. Now, we have to go backwards by half-lives to figure out how old this is. So let's go back by one half-life. If you go back by one half-life, then the amount of carbon you would have would then double if you go backwards in time. So 3.125 times 2 would be 6.25%. So 6.25% of carbon-14. If you have 6.25% of carbon-14, well, how much of the nitrogen would you have? It would be 100 subtract 6.25. So I believe if we calculate that, 100 minus 6.25 would be 93.75%. So that's nitrogen. Let's go back another half-life. So go back another half-life, the amount of carbon I had would have been twice as big. So 6.25 times 2 would then be 12.5. That's my carbon. Nitrogen. How much nitrogen would you have? Well, you'd have 87.5% because these two numbers need to add up to 100. Let's go back another half-life. Going back another half-life, we double the amount of carbon. So now I'd have carbon, 25%, and I'd have nitrogen, which would be 75%. Let's keep going back. If we go back another one, we'd have carbon, 50%, and then we'd have nitrogen, 50%. I'm almost where I need to be. If I go back one more time, then what I'd have is I'd have now 100% of carbon. Okay, we need to count the number of half-lives that have passed here. So a lot of them have passed in this question. So if we count this, I'll just do it in purple. How many half-lives have passed? 1, 2, 3, 4, 5. 5 half-lives have passed. So to figure out the age, what I would do is I would take the number of half-lives, which is 5, and then multiply by, well, how long is one half-life for carbon-14? And I believe that number was 5730 years. If you multiply those together, so 5 times 5730 years would be this fossil that you found in this rock layer would have been 28,650 years old. So that's how I'd solve these problems. Create a flow chart. Start off with like what percentage of like your uranium, lead, carbon, nitrogen you have, and then just try to work backwards until you can get 100% of either the carbon or the uranium, and then count the number of half-lives and then multiply by the age of one of those half-lives. Okay, so we talked about a lot today. We talked about how we can look at the age of rocks relatively speaking, and absolutely meaning the exact age of rocks, and we just briefly talked about the geological time scale. So again, just complete the assignments called Geologic Time and Geological Time Skill Builder, and I will talk to you next time in the next unit of study.